Hello everyone, welcome to this session. In this session, we will be dealing with the series of lectures on decoding the eye movements. So, the basic thing we all should know is why do eyes move? Why do eyes move? Why the eyes move is the main reason is to solve the problem of information overload on the brain. So, a large field of vision allows an animal to survey the environment for food and to avoid predators, thereby increasing its survival rate. Similarly, the high visual acuity also increases the survival rate by allowing an animal to aim at a target more accurately, leading to higher killing rates and availability of more food. However, there are simply not enough neurons in the brain to support a visual system that has a higher resolution over the entire field of vision. So during evolution, because of these competing demands for the higher visual acuity as well as the large field of vision, an effective strategy is needed so that the brain will not be overwhelmed with the large amount of visual inputs. If you see the rabbit eyes can move almost like 360 degrees. And we all know the rabbit is an afoveate animal. So these animals like rabbits, they give up high resolution. They don't want high resolution, but they want the larger fields of vision so that it can escape from its predators. Okay. Whereas the hawks have narrowed their field of vision in favor of high visual acuity. They have very high visual acuity, and its visual acuity is as good as 20/2, about 10 times better than the humans. So these are the strategies that are being developed during the evolution. But in humans, rather than using one of the above strategies, like either large field of vision or high visual acuity, the retina developed a very high spatial resolution in the center, what we call as fovea, and a much lower resolution at the peripheries of the retina. So you have the best resolution at the fovea and little less resolution in the periphery. So this adaptation is called as foveal compromise strategy. So this solves the problem of information overload. The object of interest has to fall on the fovea, and the image is relegated to the low resolution retinal periphery. So if you see this archery board, if you want to score 100 points, so you need to focus on the yellow circle, rather ignoring all other circles where you should hit your arrow or your gunshot. Right? If you wish to focus more on the entire field of vision there, like the yellow one, the purple one, the blue one, and the black circle, you can see everything, but all the areas are not that clear. So, the evolution of a mechanism to move the eyes is therefore necessary to complement this foveal compromise strategy by ensuring that an object of interest is maintained or brought on to the fovea. So for this, 6 types of eye movement systems have been developed in the human eye. So these 6 eye movements can be divided broadly into 2 different classes. The first one are the systems that direct the fovea on the object of interest. So what are these systems? The saccadic system, the smooth pursuit system, and the virgin system. The second set of eye movements, they hold the images of targets steady on fovea. These are the picture system, the vestibular system, and the optokinetic system. The first set of movements directs the fovea onto the object, whereas the second set of systems will hold the image of the target steady on the fovea. So, those systems that direct the fovea onto the object of interest are the saccadic system, the smooth pursuit system, and the virgin system. So the saccadic system brings the object of interest rapidly onto the fovea. The eyes moves very rapid so that the object of interest is brought onto the fovea. The smooth pursuit system holds the image of a small moving target on the fovea. It follows the object. The smooth pursuit system. The virgin system, it moves the eyes in the opposite direction so that the images of the single object are held simultaneously on both fovea. It could be of convergence or divergence, and we'll be dealing all these systems individually and in much detailed way. Right. The systems that hold the fovea on the object of interest, as we all know, they are the fixation system, the vestibular system, and the optokinetic system. The fixation system holds the image of the stationary objects on the fovea when the head is immobile. So that is, when the head is not moving, the fixation system holds the image of the stationary object on the fovea. The vestibular system holds the image of the target on the fovea during brief head movements. If the head is moved with high frequency for a very short time, then the vestibular system comes into play. Next is the optokinetic system. This optokinetic system holds the image of the target on the fovea during sustained head movements. Right? When the head is immobile, the fixation system will be playing a role. When the head moves briefly, then your vestibular system comes into play. When there are sustained head movements, to hold the image on the fovea, your optokinetic system will come into play. So these explain the thing that why should the eyes move. So why should we learn this particular topic, like why should the eyes move? By dividing the eye movements and by knowing why the eye should move, it is easier for us to localize a lesion, and we can design customized approach to the individual eye movement strategies. Like, for example, the lesions in the parapontine reticular formation results in ipsilesional horizontal sucker loss. Don't worry about this. We are going to dwell in detail about these stuff. So the lesions of parapontine reticular formation results in ipsilesional horizontal sucker loss, whereas the lesions in the abducens nucleus area in the pons affect all ipsilesional horizontal eye movements like saccades, pursuits, and VOR. That is, a lesion in the TPRS affects only the horizontal saccade, whereas the lesions in the abducens nucleus affects all ipsilesional horizontal eye movement. So with this, we complete the section and we'll move on to the next topic. Thank you.